Hi, everybody. Welcome to our first Vodcast of Chapter 7. And in Chapter 7, we're going to be discussing the topic of similitude, dimensional analysis, and modeling. This is a very important technique for understanding fluid flows, fluid behavior, because as we've mentioned a little bit about some of the computational fluid dynamics equations that we use, such as the Navier-Stokes equations, the equations are, for the most part, partial differential equations, second-order partial differential equations that don't have explicit solutions. So, quite literally, we do not have enough analytical math to describe most fluid regimes. So we rely on a technique, I always refer to this as the trifecta, where we have analytical math, similitude, and dimensional analysis, which is kind of the same, and simulation or modeling. Modeling can be very simple, just like equating one thing to another or deciding what parameters are going to be similar or important, or it can be something very complicated. For example, if you are a civil engineering student and you have to develop a water system for the town of, say, Worland, Wyoming, you have to take into account how much water is going to be available at different times, what will happen if the power goes out, what will happen if there's a major fire, where water will become stagnant, where we get those stagnation points, because in a fluid flow system, it's possible to have points where the water will be stagnant. And generally speaking, in municipality water delivery, there are requirements that the water move in certain amounts of time. For example, it can't stay stagnant for more than 36 hours. So you have to design for those things. So it can be very simple, it can be very complicated. If you're a petroleum engineer, the models get complicated in other ways. For example, if you're looking at oil moving through reservoir rock, you have pore pressure, you have more than one phase of fluid. So in other words, the fluid could exist as a liquid and a gas. You could have oil and water and perhaps other contaminants as well. So those types of things are very difficult, if not impossible, to describe analytically, and you have to use modeling tools. So the trifecta for fluid mechanics is analytical math, similitude and dimensional analysis, and modeling. So in this chapter, we're going to talk about similitude and dimensional analysis. We'll mention modeling, but the modeling that we're talking about is really about developing parameters that will allow us to describe fluid flows rather than using computer models. Because, first of all, computer models change very quickly, and second of all, they tend to be somewhat specific to the industry that you will be involved in and the types of fluid that you will be modeling. So, having said that, let's take a look at the document camera, and we'll start talking about these ideas. So, similitude means essentially that we wish to decide what parameters are most important and then find similarities between a given fluid regime and our fluid regime. So one of the things, we've talked about several of these ideas already, but one of the things that we discussed last time was the Reynolds number. Now it turns out that the Reynolds number is very important in that in order to look at a particular fluid flows, the Reynolds number of our prototype must be very similar to the Reynolds number of the fluid regime that is in question. Now, the type of modeling that we may have seen to this point might be, we might refer to it as geometric modeling. So if you have an AutoCAD class, for example, and you need to plan out a room of some sort, you can proportion it down using AutoCAD based on the geometry. So in other words, this side might be half of this side. this side would be half of this side. Otherwise, we would change the shape if we didn't keep those parameters the same. So in other words, so that somebody could take this smaller model and gin it up to build the real deal, we have to keep the proportions of the geometry the same. Now in fluids, it's not just based on geometry. So one of the things that we have to decide is what else might it be based upon. And one of the things that turns out is that they have to have Reynolds number similarity, or they have to be similar in terms of laminar, versus transitional, or laminar versus turbulent flow. So even though the numbers may not look exactly the same, or the shape of something that we design may not actually look the same from the beginning, where we are deciding what the parameters that are important will be, up through the prototype, up through the finished product, we have to design it so that we have a similarity that goes beyond the geometric. All right, so one of the things that we could say is, for example, we may decide that for a particular type of a fluid drop in some sort of length of pipe, that the delta P, or the pressure drop, might be a function of the diameter of the conduit, the density of the fluid, the viscosity of the fluid, and the velocity with which it moves. Now, deciding what parameters are important is something that requires a little bit of sophistication in understanding what the fluid regime is dependent upon. And that's not necessarily something that we can answer at this stage of the game. And even later on, it may be something that you answer once, and then you find out that you have forgotten something, and you need to answer it again in a better way. But what parameters are important, this is very difficult. So for now, we're going to sort of work with the authors, and the authors will suggest to us what parameters are important when we are modeling different fluid regimes. And so what we're going to develop is just the technique for describing how those parameters fit. Now, that's going to be the subject of section 7.1 through 7.4. All right. Now, one of the things that we would like to do, if we talk about this pressure drop again, this delta P being a function of that, we could draw a series of different graphs if we wanted to see what that relationship looked like. So, for example, we could say the delta P is a function of velocity, and my data points look like this. So, in other words, at lower pressure drops, or at lower delta P's, we have lower velocities, or at lower velocities we have lower pressure drops, because this would be the independent variable and this would be the dependent variable, and that we have a nonlinear proportional increasing relationship. But in order to do this, we would have to keep the diameter, the density, and the viscosity of the fluid constant. We could then say, okay, well, let's take a look at another parameter. Let's look at dP, or delta P, versus the diameter. Well, we find that we have an inverse proportion between those two, as long as we keep the velocity and the density and the viscosity constant, and so on, with all of our variables that we have decided are important. So if we plot delta P versus rho, and we keep the other three variables constant, we would get a graph that looks something like this. Now, this is going to be specific to a certain fluid, right? Because we're talking about a fluid of a given viscosity at a given velocity through a conduit of a particular diameter. And then, just to finish off our discussion here, we might have something that looks like this, where as the viscosity increases, the pressure drop also increases if we keep the other variable's constant. Okay. Now, this is interesting, but if instead we could form a group where we would say delta P sub L is some sort of a function of a group of these variables. And if we could then group those variables together, see what the function looks like, and then we could change mu, for example, and d, or we could keep rho constant and change the velocity. And if we came up with this, we would have a much more general relationship. So in this particular case, we could take delta P sub L and multiply it by some of the other variables. And in this case, I'll show you how to do, this is the point of what the chapter is, or what these sections are, is how to do this and what these groups look like. But if I take delta P and I multiply it by diameter divided by density times the velocity squared, and if I plot it against some other combination of variables, which I want to be very clear, we can repeat some of these variables, but if this is the relationship, if this is the functionality that we're looking at, we only want it to appear in one place. In other words, we don't want to repeat this variable down here, because then what we're going to have is delta P in terms of delta P, and that doesn't really make any sense. But if we plot this kind of a group versus this kind of a group, we get a relationship that looks like this. Now this is much more general because, like I said, we could change rho, or we could change velocity, or we could change diameter, or we could change viscosity, and we could still use a graph like this to find out what this function looks like. So this is the way that we would write this, because we don't really have numbers to assign to these. We would say that this group, d over rho v squared delta P sub L, is some sort of a function which we call psi or pi. This isn't pi, this is phi, excuse me. And this is just a nomenclature. But what we're basically saying is that delta P times some other variables is some sort of a function of some of these variables repeated and some of them not repeated. Now, and this is actually the technique called dimensional analysis, which I'll explain in just a minute. I'll explain why it's called dimensional analysis, and then I will explain to you how to do it yourself. All right. So if you look at these terms that we've written up here, there we go. Something that you may not see right away, but let's write out the first term, d over rho v squared times delta P sub L. And let's write out this group as well. It turns out that if we look at the dimensions, which would be either force, length, and time, or mass, length, and time, remembering that force is related to mass through Newton's second law. Okay. So if we have these three dimensions, if we analyze the dimensions of each of these groups, we're going to find out that they all turn out to be dimensionless. So in other words, these groups are like the Mach number, which is an example where the Mach number is equal to the velocity of an object divided by the velocity or the speed of sound. So this is in dimensions of length per time. This is in dimensions of length per time, so that the dimensions cancel each other out and the quantity is a dimensionless group. The same is true for the Reynolds number, which we'll talk about a little bit later on, but the Reynolds number is dimensionless. And there are a lot of other groups that describe fluid flows that, in the most general sense, all of these variables, all of these groups turn out to be dimensionless. So let's check our groups here. Is this dimensionless? And this is the symbol for dimensionless, square brackets that are empty. Let's check out the first one. D over rho v squared times delta p sub L. So let's think about what the dimensions of each of those variables are. Diameter has a dimension of length. Delta P, which is a pressure, has a dimension of force per length to the third, length squared. Rho, which is density, has dimensions of mass per length to the third. And velocity has dimensions of length per time. And that quantity is squared. Now, the first thing I see is I have a mass and I have a force in the same equation, and I really want to write it in terms of one or the other. So, as a choice here, you can do it either way, but I'm going to write force as mass length per time squared. I'm going to do one other thing, which is instead of writing dimensions in the denominator, I'm going to write them in the numerator with a negative exponent, and you'll see why in just a moment. So here we have length. Instead of force, I'm going to write mass length per time squared, which is going to be t to the minus 2. And here I have L squared in the denominator, which I'm going to write as L to the minus 2. And then on the bottom, in the denominator, I have mass. Length to the third in the denominator there is going to be L to the minus 3. And here I'm going to have L to the second, T to the minus 2. Okay. Now, what this will do for me is allow me to organize my dimensions. And I'm going to write this in this form. I have 3 dimensions. I have length, mass, and time. So I'm going to tabulate or pull together all of my lengths. This is I have length to the 1, length to the 1, length to the minus 2. Now, this is in the denominator of the denominator, right? So I could put it as over length to the minus 3, or I could write it as length to the 3 in the top, and this would be length to the minus 2. Now, you know that if you add up the exponents, that it will come out to be whatever the quantity is. This doesn't look like it's working right. Length squared, force, mass, length per time squared is force per length squared. Okay, so let me just take a look at this. I think I have a little error here, but I'm going to look this up. If I add these up, I get 1, 2, 0, 3, 1, right? So I have a little something here that I have missed. I'm going to have to go back and figure out what it is. Let's look at my mass units. I have a mass in the top and a mass in the bottom. So I could say mass to the 1, mass to the minus 1 equals 0, which is the desired result. And then let's look at time. I have time to the negative 2, and I have time to the negative 2 in the denominator, which is time to the 2 in the top, and that's 0 as well. Now let's go back and look at what I have going on with length. Okay, diameter is just length. Let me just write this out. So that's length to the 1. Delta P is force per length squared. And force is mass length per time squared per mass length time squared. This is my force unit. and then it's a pressure, so that's length squared. Okay, so overall, force per length squared turns out to be mass per time squared length, which is mass time to the minus 2 L to the minus 1. There we go. Okay. So that's where my problem is. This should be minus 1 right here, shouldn't it? So this is minus 1. And I still come out with a weird number, so let me keep working on this. So I have D. This is mass per length to the third. Okay, density and volume, length squared times squared. So if I look at this, I get length to the first, length to the minus 1, length to the minus 2, length to the minus 3, length squared. And I still keep coming up with something other than what I'm looking for. This would be 0, minus 2, minus 5. That would be minus 3. So I have a little problem here with my length. I'm going to go on because I haven't seen where that problem is yet, and I don't want to spend any more time on it. The other two dimensions came out correctly, and so I'm going to go on. I'm going to move to my next group, which is this group over here, and let me see what that looks like. Okay. So let's take a look, and we have density, velocity, diameter over viscosity. All right. Now, if you look at viscosity, dynamic viscosity is in dimensions of force, time per length squared. And density is in mass per length to the third. Velocity is length per time. And diameter is length. So if I break out my dimensions here, length, mass, time, and once again I need to break this out instead of having this as force. Remember, force is equal to mass times acceleration. So force is equal to mass, length per time squared. Okay. So let me rewrite this as mass length per time squared. And if I look here, then I have, let me just simplify this a little bit, mass length squared over length to the third time. So this cancels this, and I'm left with mass per length time in the numerator. And down here, I have mass length time over length squared time squared. So that simplifies to mass time, oh, I guess I should cancel that as well, mass per length time. Mass per length time, mass per length time. Okay, so as you can see then, if I take it from these simplified groups, my length here I would have, let's go ahead and write it in this form, mass L to the minus 1 T to the minus 1 over mass length to the minus 1 T to the minus 1. And if I look at length in that way, I can say minus 1 minus the minus 1, which is plus 1 or 0. Mass would be 1 minus 1, which is 0. And time would be minus 1 minus a minus 1, which is plus 1 or 0. Okay, so everything works out except my length dimension for the first pi term. So I'm going to go back and take a look at that again. I have D. I'm just going to look at length on this one. I'm going to just solve it a little bit differently because I really have to make sure that that turns out to be correct. Okay, the issue with this is delta P sub L is not, I was just looking in your textbook, is not equal to a pressure drop, but it's equal to a pressure drop per length. All right, so what that means is the dimensions are going to be pressure, which is force per length squared per length. So it's going to be force over length to the third. So that's going to clear up the issue that we had up here. Let's just go ahead and redo it. So if I look at this dimensionally, D is L, dimensions of L. Delta P is dimensions of force per length to the third. Rho is mass per length to the third. And velocity, which is length per time, is going to be length squared per time squared. So now let's see what happens. We need to change force into, using second law, mass times acceleration, mass length per time squared. So on the top we get length, mass, length per time squared length to the third, which leaves us with dimensions of mass per length times squared in the numerator, and in the denominator we have mass, this goes away, per length times squared in the denominator. And so you can see that the lengths cancel out when you put in the proper dimensions to begin with. So I apologize for that. So when we talk about the pressure drop, we're not talking about pressure drop, just to clarify, P sub L is not equal to pressure drop, as I had initially assumed. Delta P sub L is pressure drop per length. Right. So when we get our parameters correct and the units of our parameters, excuse me, the dimensions of our parameters correct, then everything works out. All right. So what does this mean for us? Well, what it means is that in order to make the most general statements about fluid behavior, we need to create dimensionless groups. In order to do this, we need to choose repeating and non-repeating variables. Recall that if we're interested in the behavior of one variable, in particular, we want to make sure that that is non-repeating. And then we want to form our dimensionless groups so that basically we have one dimensionless group that is a function of one or more other dimensionless groups. So the matter of Chapter 7, especially sections 1 through 4, deals with how many groups do we need to describe this kind of behavior, and what do the groups look like. Now, as I said earlier, one of the more difficult things to do, one of the things that requires the highest degree of engineering analysis or engineering speculation, maybe would be a good way to put it, would be deciding what variables are needed. So we're not going to have you decide what variables are needed. The authors and I will tell you what variables are needed, and then you can go through the rest of the process so that you can learn this. And later on in your career, or later on in your coursework, you may be called upon to make that engineering decision about which properties are the most important, what variables you'll need in your dimensionless groups. But for now, we're going to assume that we start being given those variables. So if we go back to the podium PC and we take a look at your textbook, what you will find when we start talking about dimensional analysis is the idea of Buckingham's pi theorem. And the Buckingham pi theorem tells you how many groups you need to describe this relationship. And dimensional analysis is based upon the Buckingham pi theorem. And this basically has to do with degrees of freedom, if you remember this from math. But the statement of Buckingham pi theorem says, if an equation involving k variables is dimensionally homogeneous, which it has to be, these have to be dimensionally homogeneous, and more specifically, they have to be non-dimensional. It can be reduced to a relationship among k minus r independent dimensionless products, where r is the minimum number of reference dimensions required to describe the variables. Okay, so basically, k is the number of variables which you'll be given, and r is the number of reference dimensions. So in Buckingham pi theorem, you need to form k minus r groups. And those groups are called pi groups. Okay, now k is the number of variables required to model the fluid flow, and r is the number of reference dimensions. So in other words, this is almost always force length time or mass length time. So it's almost always 3. Now, occasionally it's not. For example, Mach number, length per time, length per time. The number of reference dimensions here is only 2, but this is more unusual. It's more typical that it would be 3. Now, if we were talking about electricity, so we had amps or lumens or something like this, we would have more reference dimensions, more fundamental dimensions. But in mechanics, it's almost always 3. The number of variables is k. So getting back to our example before, let's take a look at our groups. How many variables do we have? We have d, rho, v, delta p sub l, rho repeats, v repeats, d repeats, and we have mu. So we have 1, 2, 3, 4, 5 variables. So in that case, k is 5 in our example. So the number of pi groups is 5 minus 3, or 2. All right, so when we look at the example that we did, here's one pi group, and here's another pi group. So we would write this as saying the first pi group is some function of the second pi group. And the first pi group would be d delta pl over rho v squared. And in Buckingham pi theorem notation, we would say that that is some function of the second pi group, which is rho vd over mu. All right, so if you continue, if we take a look back at your textbook, you'll see that it goes through this phraseology where we have the first pi group is the function of all of the other pi groups. Now, one important thing to notice is, as I said before, if we were looking for delta p sub l, we really want it to just appear in pi 1. We don't want it to appear over here. So sometimes, almost always, that's the case. Not always, but you need to choose repeating variables so that you don't make delta pl a function of delta pl. That doesn't really help you in any meaningful way. All right, so the rest of this just talks about all of this. Now, if you go to page 389, there are the steps that you go through And this is a really nice little plan of attack for doing a problem. You list all the variables involved. Those will be given to you once again, because it's very difficult to determine what it is. Express each of the variables in the basic dimensions, which we did. Determine the required number of pi terms. That's k minus r. Number 4, select a number of repeating variables where the number required is equal to the number of reference dimensions. So if you have 3 reference dimensions, you are going to want 3 repeating variables. That's going to help you get rid of the dimensions or make everything dimensionless. The pi term by multiplying one of the non-repeatings. Generally speaking, in our example, that was delta p over delta p sub l, because that's one we wanted to look at the functionality of with respect to the others. And then we make the product. Okay, so then you repeat step 5 for each of the remaining non-repeatings if you have more than one. And then you always want to check your results to make sure that everything is dimensionless. Because just like in the example I gave you that I worked, delta p sub l had to be the pi group involving delta p sub l and the other pi group had to be dimensionless, or else this work was not valid. So what that means is that if it's not dimensionless, I have to go back and find out why. In the case that I had made not an algebraic mistake or even an arithmetic mistake. I had made an incorrect assumption about what the dimensions were of delta PL. So when I identified that mistake, then I corrected it and everything worked out fine. The last step then is to write that one dimensionless group as a function of the other dimensionless groups. All right, and so this is the basic function. This is how we did it, and the work here on page 390 and 391 is basically the work that we just did on the Vodcast. All right, now this is where they lay it out, where they take the dimensions, either FLT or MLT, and make sure that everything adds up to 0. Now, the reason is you realize that if f to the 0 power, any variable or any number raised to the 0 power is just 1. That means that we have essentially eliminated the dimensions. So if we have an unknown, in this case we had what power rho is raised to, what power v is raised to, what power d is raised to, and those were unknowns. So a, b, and c, which is the exponent of those variables, are all unknown. We want them to add up to 0. So we want each one of them to add up to 0, a, b, and c. So we run our numbers, we put it into an algebraic form, set it equal to 0. Now these are going to be overspecified, which means that sometimes you could have more than one option. If you look at these 3 equations, you can see that c has to be equal to -1 in order for this first statement to be true. Then you can plug -1 for c in here, solve for b, and then you have you have b and c, and you can solve for a. And then you know what those have to be. And that's just the process of getting the groups with the proper exponents on the variables. Now this also prevents you from breaking things up. For example, rho has to be mass per length to the third. So if you have mass, if this were, for example, squared, mass would be squared, but length would be to the -6, wouldn't it? So you have to, that's what doing it in this technique, in this order, prevents you from splitting things up and changing the dimensions of each individual variable, because of course we can't do that. All right, so this is a really good step-by-step process for creating the pi terms. Now the rest of this, we just have some examples, and then we have a little discussion here in section 7.4. And this talks a little bit about the selection of variables. Now, for fluids, like we said, not only is geometry important. Sometimes when you find your variables, you have to model it so that not only the geometry is in proportion, but you need to have proportionality of other effects as well. You need to have some sort of a you need to think about the geometry. Now, if you're building a house, geometry is pretty much all you have to think about. there are other considerations. I don't mean to oversimplify that. For example, if you're building a very large house, you may have to have, for example, 2 heat exchangers or 2 HVAC systems, because you may not be able to get the kind of circulation that you need with only one through certain sizes. So there are other considerations as well. But geometry is the major consideration in most building projects. For us, we also have to talk about the material properties when we're talking about fluids. In other words, you need to think about what's going on. If it's a non-Newtonian fluid, for example, you may have to look at the viscosity relationships. You have to look at the density. You have to look at all of the things that make that fluid unique. Later on, for example, like I said, if you're in petroleum engineering, you may need to look at when the pressure changes, what happens to the composition. Do you still have all liquid? Did you break some gas out? Is it still moving? Is it equally preferential moving through the pore system? And that sort of thing. And then we also have external effects. And once again, these are important things to think about, but they're not really something that you're going to be called upon to be conversant with at this particular time. We'll give you the variables that will make the groups come out correctly, or we'll basically tell you what variables are important in this particular fluid flow. Now, the determination of reference dimensions, like I said, it is almost always either mass length time or force length time. Occasionally, there will only, one of them won't be there. For example, like we talked about with Mach number, mass and force don't enter into the equation. So all we're working with is length and time. But that's rather unusual. It's pretty safe to assume that you're going to be working with all three unless there's something odd about the problem. So let's work a problem from the back of the book so that we can take a look at how this is going to, there's one other thing I want to say before I get carried away with that. Pi groups, in general, are not unique. Now, how they'll graph out will be unique, but you are not always going to come up with the same thing. So, for example, if we had the original equation that we were working with, we said that this pi group is a function of this pi group, and we know that everything is dimensionless. Would it not also be equally correct to say that this pi group would be a function of this? And the answer is yes, because if this is dimensionless, this is also dimensionless. It would also be equally correct, although cumbersome, to take everything to the second power, because you're still going to be dimensionless. Although if you come out with a pi group like this and you see, wait a second, everything is raised to the second power, or maybe in some cases maybe this would be raised to the fourth power and these would all be squared, you could reduce it just by, well, what it means is you've chosen too large of a value where you have this a plus b plus c equals whatever it turns out to be 1 or whatever, then you have a situation where you've chosen something that was overspecified to be larger than it needed to be. So you could make this simpler, but it is not inaccurate. So pi groups in general are not unique. You can come up with many different ways to express this. All right, so having said that, let's look at problem 7.9 in your textbook, which I don't even know what page that's on. But we'll take a look at this. Let me find it. All right, looking at the podium PC. Here's 7.9. Let me expand that a little bit so we can read it a little better. Okay, problem 7.9. states the pressure rise, delta P, across a pump can be expressed as being a function of the impeller diameter, the density of the fluid, the rotational speed, and the flow rate. And it says define a suitable set of dimensionless parameters. So this is asking us to use the Buckingham pi theorem to find pi groups that will be dimensionless to give us delta P as a function of some of these variables. All right, so the first thing is we are looking for delta P as a function of the other variables. So that means that we want to make sure that delta P is non-repeating. The other variables could be repeating, and we can choose those to get the groups that we need. But the first thing that we really need to do is to determine how many pi groups we need. Well, let's go ahead and write these out in dimensions. Delta P is force per length squared. Has dimensions of force per length squared. Diameter has dimensions of length. Rho, density, has dimensions of mass per length to the third. So we're going to have to resolve these, first of all. Omega, if you remember, rotational speed is radians per second, which is just nothing per time, or time to the minus 1. It's a dimensionless quantity already, radians, over time to the minus 1. And Q, which is volumetric flow rate, is length to the third over time. I shouldn't say time to the minus 1. Let's just say time at this point. We'll go ahead and resolve that in a minute. All right, now we can either put rho in terms of force or delta P in terms of mass. Since we did it, we put force in terms of mass last time. Let's do it mass in terms of force this time. So we know that force is equal to mass length per time squared, right? From Newton's second law, force is equal to mass times acceleration. So if we solve this for mass, we get that mass is equal to force time squared per length. Now, I'm going to go ahead and write these also with negative exponents rather than positive exponents in the denominator. So I get delta P is going to be equal to force length to the minus 2, or I could say force to the 1, length to minus 2. D is length to the 1. Rho then is going to be mass, which is force time squared per length times length to the third. So I have length to the fourth in the denominator. So density then is force time squared length to the negative 4. Omega is time to the minus 1, and Q is length to the third time to the minus 1. All right, so we have 1, 2, 3, 4, 5 variables, so K is equal to 5. Our reference dimensions, we have force, length, and time, so that's 3. Okay, so that tells us two different things. We need 3 repeating variables, and we need 5 minus 3, 2 pi terms. So that means that we're going to have delta P times some stuff is a function of some of the other stuff. And we're not going to have delta P over here. All right, so let's break out our 3 reference dimensions and add the numbers together. We have force, we have length, and we have time. And we have 5 variables. So for P, for the delta P, we have force at 1, length at negative 2. So I've finished this one. For D, we have length, sorry, not here, length at 1, For density, we have force at 1, and we have time at 2, and we have length at -4. For omega, we have time at -1. And for Q, we have length at 3, and we have time at -1. And the answer to figure this out is that well, let's go ahead and do this. Hang on just a second. Let's go ahead and break this out into pi terms with our repeating variables, because this is a little bit premature at this point. So let's go ahead and break it out this way. Let's say delta P times something, right, is going to be our pi group, pi 1. And our pi 2 group is going to be something else that does not include delta P. So if we're going to use 3 repeating variables, let's choose, and this is a matter of taste, it's not a requirement. Let's say D. We need to make sure that we include all of the terms for sure, but we don't, what 3 we choose is not that big of a deal. D, rho, and omega. So that means that we're going to take delta P raised to some power times D raised to some power times rho raised to some power times omega raised to some power. And let's just say, let's call this A, B, and C. All right, so let's find A, B, and C this way. So we're actually, what we're really doing is we're just eliminating Q from this group, and we're going to call Q on the other side. So we're going to have, this is going to be Q times dP and D, rho, and W, right? Because we've chosen Q as our other non-repeating variable. What we've really done is chosen D, rho, and W as our repeating variables, keep delta P on one side, and then Q, just because it's a slightly more complicated variable, but we could have gotten pi groups out of it the other way as well. But let's work with pi 1. All right, so now let's go ahead and work this one through. We have delta P times D to the A power, rho to the B power, omega to the C power. And we know, going back, that delta P is force to the 1, length to the -2. And since that's just raised to the 1 power, that's just to itself, those variables are going to stay the same. But D is L to the 1 power, and we need to raise that entire thing to the A power, don't we? Then we have rho, which is force time squared length to the -4 raised to some other power, B. And then last but not least, omega, which is T to the -1 raised to the C. Now here's where we want my F powers to be equal to 0, my L powers to be equal to 0, and my T powers equal to 0 as well. All right, so here we have F to the 1, and here we have F to the B, right, equals 0. So that tells me that B equals -1. So that's kind of nice, just to begin with. Now L, on the other hand, here we have -2 plus A times 1, which is A. Now this is a weird one, right? We have B times -4, so that's quite large, but -4B. And then we don't have any L over here, so those have to add to 0. And we already know what B is, right? We know that B is equal to -1. So that means that here we have negative 2 plus a minus 4 times negative 1 equals 0. Negative 2 plus a plus 4 equals 0. A equals negative 4, if I bring it over here, plus 2. So a is equal to negative 2. And then for time, I have 2b minus c, and those have to equal 0 as well. And so I know what b is, 2 times negative 1 minus c equals 0, or equals c, negative 2 equals c. All right, so what that means is what I get for my first pi group then is pi 1 is going to equal delta p times d raised to the a times rho raised to the b times omega raised to the c. Or to write it in a better way, I could say delta p over d squared rho omega squared equals pi 1. All right, so I have a dimensionless group, and if I check that out, I'll see that it is indeed dimensionless, and that's pi 1. Now let's go through our pi 2 group. Pi 2, I'm going to have my other non-repeating variable, which I've chosen as q. And I'm going to have my repeating variables, d raised to a. This is going to be a different a, right? So I would really, well, I'll just go ahead and call it a. Rho to the b and omega to the c. All right, so continuing this same way then, we know that q is, and we're going to keep that repeating variable to the 1 power if we possibly can. That's one way to avoid getting large exponents, larger than necessary exponents. Okay, so q has dimensions of L to the third t to the negative 1. And d has dimensions of length to the 1. That's raised to the a power. And rho, written in force length time, is force time squared length to the minus 4. It's raised to the b. And then omega is t to the minus 1 raised to the c power. All right, so once again, we break down force, length, time, and we want all of our exponents to add up to 0. So here is the only place, this is interesting, isn't it, where we have force raised to the b power. Well, I guess I could just say b. There's no other force occurrence, so that's equal 0. So what does that tell you? Well, that tells you that this term is not part of the pi group. Okay, so if this goes to 0, that means that we really don't need it in the second pi group. So it's just going to look like that. So continuing then with length, here for q, we have a 3. For the diameter, we have a. And here we have negative, well, that goes away, doesn't it? Because we have negative 4b, but b is 0. So this is going to equal 0. So that tells me that a is equal to negative 3, or the dimensions of the diameter are going to be the third power. And last but not least, we have time. We have negative 1 minus c equals 0. So that tells me that minus 1 is equal to c. All right, so if I form pi 2 then, I get, like I said, the density is irrelevant. So I get q, which I've sort of set at 1, times d to the negative 3, times c to the minus 1, excuse me, omega to the minus 1. And to write it in better form, q over d to the third omega. All right, so then check that out. Everything works out. And my answer then is pi 1. To write it in this form, pi 1 is some function of pi 2. Or my first pi group, delta p over d squared rho omega squared is some function of Q over D to the third omega. All right. And so that solves that problem for problem 7.9. There are several problems that you will run through for Buckingham pi theorem for this section. For these sections, 7.1 through 7.4, they all play out about the same way. And when you get done with them, I think you'll be very good at determining the dimensionless groups using this process. So that's it for Vodcast 21. We'll see you back here for Vodcast 22.